All right, so when it comes to elasticity, not only can we use forces to solve problems, we can also use energy to solve problems. And typically speaking, you're going to always want to pick energy whenever you have the opportunity, simply because it makes dealing with these problems significantly easier. So here's a typical example problem. We have a 10 kilogram mass that's initially suspended from a vertical spring, and it's suspended initially in such a way in which it is elastically displaced 15 centimeters from its equilibrium position. Right? In other words, it starts down here, a little bit stretched from this horizontal red line, which is its equilibrium position. So when you let it go, it's going to go upwards to try to recover its equilibrium position. Now, the spring constant here is provided to you, and what you're asked to find is the speed of the mass at the equilibrium position if it is initially stationary after it is displaced. All right, so this is a problem that you really want to be able to go through and solve. Now, in order to do this, what I recommend you do is use energy. Now, how you organize yourself is up to you, but what I like to do is I like to make myself a chart to keep track of all of the different types of energy. This basically makes your life a little easier because it allows you to ask yourself one question at a time as opposed to trying to build systems of equations. So if you're going to organize yourself this way, we always have types of energy. We have initial amounts of energy, if I can spell it right, final amounts of energy, and lastly, the change, or delta column. However, the start of every energy problem is always exactly the same. Take a look at this particular problem and ask yourself how many different types of energy are present. Please pause the video. I'll pick it back up in a couple of seconds. All right, if you've taken a look at this particular problem, there are three different types of energy that you should have. And you can figure out which ones are present here. There's a couple of questions you should always be asking yourself. The very first one is, does it move? Well, at the end of the day here, you're asked to find the speed of the mass as it comes back to the equilibrium position. Because you're asked for that, it probably does move at some point. The minute you said yes to that, one of your types of energy will be kinetic, and for kinetic energy, we always have the same equation, where it's equal to 1 half mv squared. Right, so that's one of the types of energy that you will most definitely have here. As for the other ones, you got to ask yourself, well, is there any forces present here that are going to give me energy and take them away? And the answer is there are definitely forces here. Number one, you stretch the spring. The minute you stretch the spring, there is a potential associated with that stretching, and that is the spring potential. And that will be a second type of energy that you have here. And in the lectures, we talked about the spring potential. The spring potential, the amount of energy you have, can be found by taking 0.5, multiplying it by k, and multiplying it by the displacement from equilibrium, all squared. Right, so that is a second type of energy you have here. You also have a third type of energy here. This third type of energy here comes from the fact that we actually have a second force here that we're going to be displacing against. This one here is actually the force of gravity. Just like with the previous example, gravity does act on this entire system. Oops, let's not change the line. And if it's there, it's going to have its own potential. So there is a gravity potential here. Now this gravity potential here can be found by using the force of gravity and the displacement. The change in potential for gravity, as it is a constant force, one second here, is force dotted with displacement. Right? I don't have a dot symbol here, so you're going to have to deal with the word. Now, both these forces and displacement are vectors. Now, just like before, this delta change in gravity means that you can simply ignore the initial and final states and calculate the change directly. Notice here that the spring potential is not a change in potential. It is an absolute potential because it has a well-defined 0 point, and that 0 point is when we are not displaced from equilibrium. Now, when you have this, your goal, therefore, is to see how many different types of energy that you can fill in based on what you know. So if you take a look at this problem, you're told a bunch of things. We're going to start up at the kinetic one. Taking a look at a kinetic energy, you're told one thing that is incredibly relevant here. You're told that it is initially stationary. The minute you see initially stationary, they're telling you that the initial velocity or the initial speed is 0. If that's the case, you can fill in the initial amount of kinetic energy immediately. As for the final amount of kinetic energy, you can't fill that in because you do not know the speed of the mass at its final point in which the mass is returned to equilibrium. So for this top type of energy, kinetic, we're actually done here. There's nothing else we can fill in at this moment. So we're going to work our way down to spring potential. Now, for spring potential, you're told a couple of things. First of all, you are told that we start out at the very beginning displaced 15 centimeters from our equilibrium position. In other words, our initial displacement from equilibrium is 0.15 meters downwards. All right, so with that, we can actually find the initial spring potential. So if we want to find the initial spring potential, what we can do is we can find the initial spring potential. I'm going to do this up at the top just so we got space for it. And this can be found by taking 0.5, multiplying it by k, which is 10,000, and then multiplying it by the magnitude of our displacement from equilibrium squared. All right, so putting this all together, we can actually turn this initial displacement from equilibrium into a finite number of joules. If you multiply these all out, what you will get is you will get an initial spring potential of 112.5 joules. All right, and once you've found that, you can literally go back to your organizational chart and you can fill in 112.5 directly into this initial spring potential. Now, the second thing you're told is that the mass is returning, right, to its equilibrium position. Returning to its equilibrium position means that for the final state, your displacement from equilibrium when you're looking for the final speed is 0. If you've been following along, if in our final state our displacement from equilibrium is 0, our spring potential in the final state must also be 0. Because if we take 1/2 times k times the displacement from equilibrium, if the displacement from equilibrium is 0, we're going to get 0 here. So you can actually fill in the final amount of kinetic energy. It's just going to be 0. Now, lastly, working our way across the row, it is also possible for us to fill in the change in potential. We know that the final potential is 0. We know that the initial potential is 112.5 joules. So we can fill in the the change in spring potential simply by taking final and subtracting initial. 0 minus 112.5 is simply negative 112.5 joules. And for this orange spring potential column, we've actually filled the entire thing in. Right? The very last thing that we need to do here is work our way down to the gravitational potential. Now, for the gravitational potential, we have the gravitational force. This is exactly identical to what we found in the last one. And we have the displacement. This thing is actually going to go upwards, right? Because it's been stretched downwards by 0.15 meters. And so when it travels from its initial position back up to its equilibrium position here, it's actually going to go upwards. So putting these together, we know that the force of gravity here is going to be 0 in the x and negative 98 in the y. And our displacement is going to be equal to 0 in the x and 0.15 in the y, both of which are in SI units. Now, once we have this, we're going to find the change in potential due to gravity due to gravity here directly. We do so by dotting together the force of gravity and the displacement. To do a dot product, simply take the two x things and multiply them together. 0 times 0 is just 0. We're going to then add to that the two y parts multiplied together. Now, if you take these two y parts, please be careful with the sign. Multiplying them together will give us negative 14.7. So we can remove this here and just have a subtraction. Now, putting these together, 0 minus 14.7 is going to give us negative 14.7. However, keep in mind there is a negative sign in front of the dot product that we have to deal with. So putting these all together, we'll get positive 14.7 joules. And we can actually stick that directly in our chart as 14.7. Now, once we're here, the problem-solving process is simply to fill in everything that is present, because every energy problem is basically some type of problem-solving type thing. So I'm just going to slide this over so we have a little more space to work with here. Our goal is to fill in through inference everything else that we can. The first thing we can fill in is we can actually fill in the change in kinetic energy. We can fill in this change in kinetic energy because I know that the change column all has to add up to 0. The only way that works is if this change in kinetic energy is 97.8. How you know is because we need this change column to add up to 0. 97.8 is the only number that can be combined with negative 112.5 and 14.7 to give us 0. Right, so basically we can infer what the change in kinetic energy is. Now, with that being said, I can also infer what the final kinetic energy is. The final kinetic energy here needs to be 97.8 as well, because for this chart we need final minus initial to be equal to the change. Now, once you have this chart filled in, there is one final step to deal with, and that is one of these types of energy is going to help you solve this problem. Now, at the end of the day, what you're asked to find is the final speed. So please pause the video here and give yourself a couple of seconds. Out of all of these types of energies that we filled in, which one is going to help you find the final speed? Now, if you've done this, we are looking for the final kinetic energy. So if we're looking for the final kinetic energy, we should probably be using something in the final column. Or sorry, if we're looking for the final speed, we should probably be using something in the final column. And because we're looking for a speed, it has to deal with motion. Sorry, that yellow is awful. So we're going to want to use the final kinetic energy. And this helps us solve our problem because at the end of the day, this final kinetic energy has to follow our characteristic kinetic energy equation. So no matter when we look at it, we need Ek to equal to 1/2 mv squared, no matter when we look at it. At the end of the day here, I know that the final kinetic energy needs to be 97.8 joules. I know that the mass here is 10 kilograms, and that leaves me with just V to find. Again, this is going to give you a single equation that you can solve. And this equation is literally going to tell you what the answer is. Now, if you've done this correctly, hopefully I have, you never know, I get about 4.42. And because we're in SI units, this will be in meters per second. All right, and once you have here, you're basically finished. All right, so this is the answer that you want, and it gives you the final speed once you're all said and done. So what you'll notice here is, again, about energy. One of the best things about this is if we take the time to organize ourselves properly, we can actually solve a problem involving multiple different elements in a rather short order. And that's the strength behind it. All right, so this type of energy thing is not going to go away. From now until the rest of the year, we're just going to be introducing new types of forces and new types of energy. This will conclude lesson 17. This example is fairly lengthy, but it is something that you can work through and do.